Hello everyone, welcome to a really exciting chapter, the formation and structure of stars. So today we are going to explore how stars are actually born and what's happening inside them. Now think about this for a second. Every single star you see in the night sky, including our sun, started out as just clouds of gas and dust floating in space. So, how does something so cold and dark turn into something so bright and powerful? And that's what we are going to uncover in this chapter. So, by the end, you will see stars not just as twinkling dots, but as living, evolving systems with their own life stories. Now, before we jump into the details, let's look at what you will be able to do after finishing this chapter. So, by the time we are done, you will be able to explain how stars form, how they stay stable, and how they make their energy. In other words, we will go from the very beginning, a cloud of gas, to the engine that powers the universe. So, as we move through this chapter, keep asking yourself, what forces are at play here? And how do they balance to create something as complex as a star? Okay, now let me give you a quick roadmap so you know where we are headed. So let's start by looking at how stars are born from the interstellar medium, those massive clouds of gas and dust we talked about last time. And then we will explore what's happening inside a young star, how gravity, pressure, and temperature interact to create balance. And finally, we will dig into how nuclear fusion, the process at the core, provides the energy that keeps a star shining for millions or even billions of years. So it's going to be a journey from cold space dust to the blazing heart of a star. So let's begin right at the start. We are the birthplace of stars, the interstellar clouds. Alright, now let's start exploring how astronomers find regions where stars are forming. Now, before I explain, here's a question for you. What kind of stars do you think we can use as signposts to identify star forming regions? The answer is O and B stars, the most massive, hottest, and brightest main sequence stars. And these stars emit enormous amounts of ultraviolet radiation. So, why is that important? Because UV light ionizes the surrounding gas, making it glow. And that's why in this image, you can see pink emission nebulas. That's gas glowing from the UV radiation. And notice the blue regions. Those are reflection nebulas, where dust scatters the starlight. Now another question. Why do astronomers focus on these massive stars and not smaller ones? The reason is that when these stars are short-lived, living only a few million years, and that's extremely brief compared to a star like our sun, which lives billions of years. And because these massive stars die so quickly, they don't drift far from where they formed. So if we see them, we know the star formation there is current, ongoing, and nearby. So they are literally cosmic signposts for stellar birth. Now let's talk about the nebulas themselves. Look closely. The bright regions show glowing gas illuminated by those young stars. But there's also dark regions where dense clouds of gas and dust are hiding stars still forming inside. Now here, the dense dark nebula are on the right side near the emission and reflection nebulas. So these regions often contain protostars. Protostars means stars in their very early stage, still hidden from view in visible light. And don't miss the left side of the image. You can see a supernova remnant, clouds of hot gas expanding after a massive star's explosion. And it shows us that star formation is part of a large cycle. Stars are born in these clouds, and when massive stars die, they can trigger formation in nearby clouds through shock waves. So, in one image, we can see a full picture of stellar life in action. Newly formed O and B stars lighting up gas and dust, dense regions hiding protostars, and a supernova remnant reminding us that star formation is part of an ongoing cosmic cycle. Now let's dive deeper into the giant molecular clouds, the actual nurseries where stars are born. First, take a look at this infrared image of NGC 346 from the James Webb Space Telescope. Now before I explain, here's a question. What do you think we can see in infrared that we cannot see in visible light? It is the coal dust and protostars hidden inside dense clouds, right? So even though the clouds are extremely cold, just a few degrees above absolute zero, they have enough material packed into them to eventually form stars. And the molecules like H2 are the basic building blocks. Now look at the blue areas in the image. These represent silicate, dust and complex molecules, showing where the dense material exists inside the cloud. And each GMC means giant molecular clouds, has tens of thousands to millions of times the sun's mass. So this means one cloud can give birth to entire clusters of stars over time. Now notice the bright filaments and patches in the image. Those are regions rich in dense cores where multiple stars are forming simultaneously. Now to put that in perspective, one parsec is about 3.26 light years. So these clouds can span hundreds of light years across, making them massive structures in the galaxy. And next, extremely cold temperatures mean the gas moves very slowly, which is important because it allows gravity to overcome thermal pressure and start the collapse of dense cores. And even though these clouds are dense by interstellar standards, the gas is still incredibly diffuse compared to a star's interior. Yet, it is enough to form dense cores that will become stars. Now here in the image, the faint diffuse red regions in the image represent warm dust heated by young massive stars. So this area shows how some parts of the cloud have already begun forming stars, while surrounding cooler material remains dense but not yet collapsed. And these are small pockets inside the giant cloud where gravity has concentrated enough matter to begin forming a star. So this is why a single GMC can produce a whole cluster of stars. Here the bright spots and filaments in the image highlight these dense cores. And some of them are already heating up and emitting infrared light, which is why we see them in this James Webb Space Telescope image. And notice here the red represents the diffuse emission from warm dust near massive young stars. And the blue areas trace cooler silicate dust and molecules. Next, the bright filament indicate dense cores where protostars are forming. So this image gives us a three-dimensional sense of where star formation is happening inside the cloud. Alright, now that we understand where stars form and the giant molecular clouds that serve as stellar nurseries, let's explore why star formation doesn't happen instantly everywhere. Even in these dense clouds, there are forces that resist gravitational collapse. So what do you think? What forces do you think that resist gravitational collapse? Let's learn, okay? Now gas particles are always moving even at very low temperatures. And this motion creates pressure that counteracts gravity, and that's about 780 miles per hour. So gravity must be strong enough to overcome this motion to pull the clouds together. So why can't cold clouds collapse immediately? Because even slow moving particles exert thermal pressure that resists compression. Now here look at NGC 2035 again. Focus on dark dense regions. So these are areas where thermal pressure is just one of the factors resisting collapse. So gravity has to overcome this outward push for a dense core to form. Now the interstellar medium has a magnetic field, and although weak compared to Earth's, it can slow these motions of charged particles. And the neutral gas can slip past magnetic fields more easily. So in some parts of the clouds, ions recombine with electrons, reducing magnetic resistance and allowing contraction to proceed. So you can think of the magnetic field like a spring inside the cloud. Charged particles get tangled, resisting collapse. But neutral gas can slide past and slowly start forming stars. Now as a cloud contracts, it spins faster. Just like an ice skater pulling in their arms, they spin faster, right? And this spin creates outward forces opposing gravity. And strong currents and chaotic motions twist the gas, making it harder for gravity to pull the cloud into a single dense core. So if gravity is stronger than all these forces, what happens? Then collapse begins, and dense cores form, starting the process of star formation. Alright, now so far we have learned that cloud faces several forces resisting collapse: thermal pressure, magnetic fields, rotation and turbulence. But still star formation does happen. Now the question is, what pushes a cloud over the edge so gravity can finally take over? And one of the main triggers is shock waves. So what is a shock wave? A shock wave is a sudden disturbance moving through the interstellar medium. And when it hits a cloud, it squeezes the gas, increasing its density abruptly. So this sudden increase can overcome the resisting forces we just discussed, like thermal pressure and magnetic fields. Again, you can think of it like squeezing a sponge. The cloud resists a little at first, but the shock waves pushes enough to make parts of it collapse. Now here this figure shows a sequence of 5 visuals. Notice the first top panel. The red shock wave is approaching the gas cloud, and by the second panel, the wave has passed through, compressing the gas. Next, in the fourth panel, it highlights regions that become gravitationally unstable. And finally, in the fifth panel, contracting gas regions start forming stars. So now we know what shock waves do. Alright, next let's look at the sources that creates these waves. First, when a massive star dies, it explodes, sending a powerful shock wave into nearby clouds, and then compressing the gas and triggering star formation. Simple as that. And even living massive stars push on surrounding gas. So they create shocks that compress parts of the cloud. And next, hot young stars ionize nearby gas, and this expansion produces pressure at cloud edges, triggering collapse. So these sources show that both dying stars and living stars can trigger new star formation, creating a chain reaction in the cloud. And once the cloud is compressed, it forms dense cores, which are the seeds of new stars. Now compressed regions form dense cores that may collapse into protostars over a few million years. And astronomers see young stars in areas predicted to be shock compressed, confirming that shock waves trigger star formation. How amazing is that, right? Now in here, the final bottom panel shows dense cores glowing inside the cloud, representing protostars forming after compression. So we can say that shock waves are a primary way clouds start forming stars. So now we just saw how shock waves can push a cloud over the edge to form stars. But star formation doesn't just happen from one source. It can be triggered in several ways across a cloud or even a whole nebula. Now, as we discussed before, when a massive star reaches the end of its life, it explodes as a supernova. And that explosion sends a strong shock wave through space, compressing nearby gas clouds. So you can think of it like dropping a heavy rock into a compound. The ripples push things along. And here, the shock wave pushes gas in the cloud, creating dense pockets that can collapse into new stars. And these compressed regions form dense cores that may take a few million years to collapse into stars. But it's only dying stars that can trigger star formation. Sometimes all clouds collide, and that can also spark star birth. So when two massive molecular clouds collide, the gas at point of contact gets squished together. It's just like two snowballs crashing into each other. The overlapping part becomes denser than the rest. And these high density regions often become the seeds for multiple new stars forming simultaneously. And finally, star formation can actually spread from one generation to the next. Now, young stars don't stay quiet. They emit strong winds and radiation. And these push on the surrounding gas, compressing it and triggering the next generation of stars. Now here, look at the N44 nebula. Over 40 young O and B stars are inflating a bubble of hot gas. So the stars we see today actually formed from gas compressed by previous generation of stars. So in a nebula, star formation can ripple outward. One generation triggers the next, spreading star formation through the region. Now here you can see both images side by side. On the left, figure A shows a supernova shock compressing a cloud, and on the right, figure B shows the N44 nebula, where new stars are forming sequentially from earlier stars' effects. Alright, now that we have seen the main triggers of star formation, shock waves, cloud collisions and sequential formation, let's move on to what actually happens inside these clouds as they heat up and contract to form stars. So let's look inside these clouds and see what happens as they start to heat up and collapse. So this is the step where a cloud really begins its journey toward becoming a star. Now as the gas in a dense core falls inward under gravity, the atoms speed up and collide with each other. Then these collisions turn motion into thermal energy. So the gas heats up and pressure increases. It's just like when you rub your hands together really fast, they get warm because the motion turns into heat. And similarly, falling atoms heat the gas. So gravity doesn't just pull the gas inward. It also warms it, setting the stage for star formation. And even though the gas heats up, it can still lose energy by emitting infrared light. So dust and molecules carry this energy away, letting the cloud keep collapsing. Again, you can think of it like letting steam escape from a pressure cooker. The cloud stays cool enough to keep contracting even while gravity keeps heating it. Now this cooling is essential. Without it, the cloud would heat up too quickly and stop collapsing. Now the rate at which the cloud collapses depends on the balance between heating from gravity and cooling from radiation. Too much heat slows contraction, but efficient cooling lets it proceed faster. And during this free fall collapse, dense protostar cores gradually form inside the cloud, setting the foundation for a future star. So the cloud is not just falling inward, it's actually converting gravity into heat, radiating energy, and forming the first dense centers of a protostar. Now, even though we have shown this figure before, here you can imagine the same sequence. Compressed gas start heating as it falls inward, infrared cooling lets it continue contracting, and dense core gradually appear inside the cloud. Alright, now that our cloud has collapsed and heated up, we have reached the next stage in a star's life, the protostar phase. So this is when the forming star is no longer just a cloud, but not a quite true star yet. So let's see what happens during this fascinating transition. Now as the collapsing core grows denser, it becomes opaque, meaning light cannot easily escape anymore. And the energy from contraction gets trapped inside, which slows down the collapse. Now let me explain. It's a bit like when you wrap a blanket around a warm object. The heat can't escape, so it gets hotter inside. So at this point, the protostar is forming deep inside its cocoon of gas and dust, invisible in normal light but bright in the infrared. Now on the right side of this figure, we can actually see this happening in the Orion Nebula. Those faint glows in infrared are hidden protostars warming up inside dusty clouds. Now since fusion has not started yet, the protostar's light comes from gravitational contraction. As gas continues falling inward, energy is released as heat and radiation. So the star is glowing, but it's not yet burning hydrogen. It is basically shining because it is still falling in on itself. And even though it's relatively cool, its total brightness can be surprisingly high, sometimes more luminous than the sun, because it is still large and radiating lots of energy in infrared. So that's why infrared telescopes are so useful. They can detect these hidden baby stars long before they are visible in ordinary light. Now, as the protostar continues shrinking, its core temperature and pressure rise rapidly. And once the temperature hits about 10 million Kelvin, hydrogen fusion finally ignites, making the birth of a true star. It's like turning on the pilot light. After all that build-up, the first nuclear reactions finally start, and the protostar joins the main sequence. Now here on the chart diagram, you can see this evolution. The dashed arrow shows how a protostar is cool and bright in the upper right, then moves down and left as it contracts and heats up, and finally settling onto the main sequence. So here panel A on the left shows the protostar's journey on the chart diagram, starting cold and dim deep inside the cloud, then heating up until fusion begins. And panel B shows real protostars in the Orion Nebula glowing in infrared light, hidden in visible light but shining clearly once we look with the right instruments. So at this stage, we finally have a newborn star. Fusion is starting, but it's still shedding the last of its dusty cocoon. Okay, we have now reached the big moment. Our protostar has grown up. This is when the hidden baby star finally becomes visible and enters the main part of its life as a true star. So let's see how that transformation unfolds. So after millions of years of contraction, the core temperature finally hits around 10 million Kelvin, hot enough for hydrogen fusion to begin. And once fusion starts, it produces an outward pressure that perfectly balances the inward pull of gravity. So we call this balance hydrostatic equilibrium. So think of it like a tug of war that's evenly matched. Gravity pulls inward, fusion pushes outward, and the result is stability. the star stops shrinking and finds its balance. Now, this is the defining moment when the protostar becomes a main sequence star. It's finally shining because of fusion, not contraction. Now that fusion has kicked in, the young star becomes very active. It releases powerful stellar winds and radiation that blow away the surrounding dust and gas cocoon. Now imagine a newborn star literally clearing its nursery. The radiation pushes the dust aside and suddenly it can be seen in the visible light for the first time. So that's why when we look at regions like the Orion Nebula, we see some stars still hidden in dust while others are fully visible. They have just cleared away their envelopes. Now once the dust clears, the star settles into the main sequence, the long stable phase where it spends most of its life steadily fusing hydrogen into helium. And the leftover material that doesn't get blown away can form a rotating disk. And from that disk, planets, moons, and asteroids can eventually form. So, in a way, when a new star is born, it's also the beginning of potential new solar systems. Now, here in the Orion Nebula, you can see this transformation in action. Some stars are still glowing only in infrared, hidden inside dust, while others, the young, newly visible ones, shine brightly in optical light after clearing their surroundings. Now, this is the moment where stellar infancy ends and true starlight begins. So, now we have a fully formed young star shining steadily in visible light. And from here, it will spend billions of years on the main sequence, just like our Sun, a calm and stable phase before the next great transformations later in its life cycle. Alright, now with this, we conclude section 1 from our chapter. So to wrap up this section, we have followed the incredible journey of how stars are born. It all begins deep inside cold, dark molecular clouds, where gravity slowly overcomes the forces resisting collapse. And sometimes shock waves from supernova or stellar winds give that extra push to start the process. And as the gas collapses, it heats up, forming dense cores that become protostars. And eventually, the temperature in the core rises high enough for hydrogen fusion to ignite, the moment a true star is born. And next, the young star then clears away its dusty cocoon and shines visibly for the first time, marking the start of its stable main sequence life. Alright, now next let's move into section 2, where we will explore how these newborn stars group together into clusters and associations, giving us even more clues about how stars form and evolve.